All right, so today we're going to learn about good old, get out of here. Thermochemistry. Okay, and thermochemistry is the study of heat changes that accompany a reaction, a chemical reaction. Okay, and when people put thermochemical equations out there, they always put them kind of like this. So this would be for like a heat pack, okay? So heat pack, so think like a hand warmer. A chemical equation would be something similar to 4 Fe in parentheses S. So 4 solid iron plus 3 O2, and that's going to be a gas. Okay, so when you mix solid iron and oxygen, you're going to create 2Fe2O3, which is a solid. Okay, so you're going to make some form of rust, essentially an iron oxide. All right, but then you also have plus 1625 Kj. Okay, this is saying that after we've done this procedure, okay, exothermic, it's giving off heat. In our products, we have an extra 1,625 kilojoules, okay? And so that is an exothermic reaction. It's giving off heat, okay? Now, if you were to look at a endothermic reaction, so say something like you have like a cold pack, okay? This stuff is going to be in the beginning, in your reactants. So you have 27 kilojoules plus ammonium nitrate, NH4NO3, okay, which is solid. And you'll also, well, you'll break that down, okay, in a cold pack. And you'll get ammonium, which will be aqueous. And you'll also get nitrate, which will be aqueous. Okay, and those are both ions. Ammonium's positive ion. Nitrate is going to be a negative ion, but our reactants have the extra stuff here, okay? The extra energy, these kilojoules. So if the energy is in reactants, that is going to be equal to an endothermic reaction. Okay, so in order for this to work, it has to absorb 27 kilojoules for this to break down into these two things, okay? If energy is in the products, that will equal an exothermic reaction. Okay, so when you're looking at those two types of things, we have that change, all right? And what we need to be focusing on is the change in energy in a system, okay? And so a system is going to be a specific part of the universe that contains the reaction or process you wish to study. Okay, so essentially the system is just going to be specific to, if you're doing a reaction in a beaker, the system is just going to be the beaker. Everything else around, everything else in the universe at that point in time is going to be called the surroundings, okay? And so what we want to look at when we're measuring this change, okay, this is essentially, you want to measure enthalpy, okay? And so enthalpy is just the heat content of a system at constant pressure, okay? And so it's really kind of hard to measure enthalpy of a substance, but we can measure the change in enthalpy, okay? So you can see what the heat was before and then see what the heat was afterwards, okay? And that's generally how people will look at it. And so what we're going to talk about today is going to be the change in enthalpy for a reaction, which is just going to be called enthalpy or heat of reaction. So enthalpy of reaction, okay? And enthalpy is delta H. So enthalpy is something we measure as an H. And then usually there is in subscript behind it, so in lowercase letters, RXN. So for this, it's of a reaction, delta H of a reaction. And I wonder, here, I'll go ahead and oh, that's not what I want to do. Undo that. I just want a line. So delta is just a little triangle. So delta H. Oh, that's a good straight line. That one was not as good. And then down here in subscript, R, X, N. Come on. Okay, so delta H RXN is the enthalpy of a reaction. All right, and so when you're looking at that change in reaction, you are looking at, so enthalpy of reaction is going to be equal to the enthalpy of the products minus the enthalpy of the reactants. Right? So enthalpy of products minus the enthalpy of the reactants. And so up here, when we look at the heating pack, okay, in the products minus the reactants, our change in enthalpy is going to be 100 or 1,625 kilojoules, okay? The change down here will be negative 27 kilojoules, okay? Because we're taking products, which would be 0, minus the reactants, which would be 27, okay? And so that's how you can look at and try and figure out enthalpy things. There's a lot of different things that we can look at, though, with enthalpy, okay? Are there any questions so far about this stuff?
So in an endothermic reaction, it absorbs the heat.
Endothermic reaction, yeah, it's taking it in so it feels colder, okay? And that's because it's taking in heat to do the reaction. Exothermic reactions give off heat, endothermic reactions take in heat. So like an exothermic reaction would be burning something, combustion, where it's going to give off heat. Any other questions? Okay. If nobody has any questions, I guess we can move on a little bit. So, also, is anybody taking notes, or can I erase this? All right, I'm gonna clear that done. So the other thing that we need to look at is kind of when we're doing like change in states with enthalpy. When you look at the enthalpy of combustion, which is going to be delta H combustion. Okay, delta H comb is what that would look like in shorthand. But the enthalpy of combustion is essentially the change for the complete burning of 1 mole of a substance. So, enthalpy of combustion, this is the enthalpy change for the complete burning of 1 mole of a substance. Okay? And so when you look at certain things, like for table sugar, sucrose, okay, which is C12H22O11, okay, which is sucrose. To burn that much sugar, to burn 1 mole of sugar, okay, it takes 5,644 kilojoules, okay, so that many kilojoules per mole. Now, in a lot of things, what you'll see, due to the fact that it is going to take, or there is a change there, for some reason with a lot of these, they like to put negatives in front of that, and so it would look like that, but essentially it's going to take that many kilojoules per mole to burn 1 mole of sugar. So if I flip forward and we look at a problem, so if you were doing this problem, a bomb calorimeter, my color, calorimeter is useful for measuring the energy released in combustion reactions. Okay, the reaction is carried out in a constant volume and these are essentially just, again, the calorimeter is like you could do one with a styrofoam cup. They're pretty similar, but a bomb calorimeter is a specific type. Anyway, so constant volume bomb with a high pressure of oxygen. How much heat is evolved when 54.0 grams of glucose is burned? Okay, and so it gives you an equation, and then it also gives you the change in enthalpy. okay, for combustion. So C6H12O6 plus 6O2, okay, is going to yield 6CO2 plus 6H2O, okay, plus the change in enthalpy, okay, is going to be delta H is going to equal negative 2,808 kilojoules. Okay, so that's essentially how many kilojoules it takes to burn 1 mole of glucose. However, we're not working with 1 mole of glucose. So what you have to do is convert the grams into moles. Okay, so 54 grams of glucose is going to be, we're going to multiply that times 1 mole glucose and 180.18 grams glucose. Okay, and so when we work that out, essentially you divide 54 by 180.18, and you're going to get 0.300 moles glucose. Okay, so now we want to figure out how much heat is used. So we know that it takes essentially 2,808 kilojoules, okay, to burn 1 mole. And we just need to multiply that times 0.3 moles glucose. Okay, I should put 0 in front of that. Okay, so when you multiply that, you'll figure out that in order to burn in this bomb calorimeter, it is going to take you essentially 842 kilojoules to burn the 54 grams of sucrose. Okay? Does anybody have questions about this? And again, it's a weird thing that they do, putting a negative. Essentially, when there's this negative right here, that means that it's exothermic. If it's a positive, it's an endothermic. I think it's essentially, the negative is the amount of heat or the amount of energy being released. So this is negative kilojoules from the original stuff. Whereas if this was positive, it would be how much energy the thing is absorbing. So negative is how much it's giving away, and then positive is how much it is receiving. But again, so like down here, you would just put it as positive. You wouldn't put it as negative. So does anybody have questions about this? Okay. And a lot of this stuff does the same thing when you're working with these change in states. So burning is one thing. You can also have molar enthalpy of vaporization or molar enthalpy of fusion. And here, go ahead. Can I erase this, or is anybody using it right now? Okay. A couple other things I'll just mention before we finish up. So we're going to have molar enthalpy of vaporization is going to be the essentially the heat required to vaporize 1 mole of liquid. Okay, and so that's going from liquid to gas. Okay, so a lot of different things have different molar vaporizations. And then you're going to have the molar enthalpy of fusion. This is essentially where the heat required to melt 1 mole of solid into liquid. Okay. Molar enthalpy of fusion. This is the heat. Okay, and so this is going from solid to liquid. All right, so you have vaporization and then you have fusion. They're all pretty different. So like water, for example, water has a delta H of vaporization, so the change in enthalpy of vaporization. You need to heat water 40.7 kilojoules, okay, for it to go from liquid to gas. But to make it go from solid to liquid, so to essentially melt ice, all you need is going to be 6 kilojoules, 6.01 kilojoules, okay? And so they take different things. It takes, to go from ice to liquid, it takes only 6 kilojoules per mole. And then once you get up into that, going from liquid to gas, it obviously takes a lot more energy to do that. Okay? Are there any questions?
Are you leaving the screen up for a minute?
Yeah.
Okay.
Yep. And I'll even, so if you don't have any questions, what I'll go ahead and do right here is I'll just type out on page 532. I would just like you guys to do number 23 and 25. Okay. And that's really all I want you guys to do for next week. Our numbers 23 and 25 in the book. And for the other kids, I will send you an email with those in it to Kyler, Joe, and Anthony. But yeah, it's pretty much exactly what we've been doing, or what I did in that one example problem. So number 23 just says calculate the heat required to melt 25.7 grams of solid methanol to its melting point. So really, you're just going to take that many grams of methanol. You'll have to change methanol into, or grams into moles, and then figure out based on how many moles you'll multiply that by the change in vaporization there. Or no, solid methanol. That'll be the change in fusion. Excuse me. So, but if you have questions, you can ask me, obviously. But if you do not have questions, then you're good to go. Like I said, Carly, do you still need this up?
No, I'm good.
Okay.
Thanks, Schultz. See ya.
See you, Schultz.
Oh, see ya.